So we learned about the importance of this init events, which is to launch the system that we are building. Can be reactive, can be distributed, can be any application domain. So once we launch the system, we will want the invariant to be established, analogous to proving the individual cases of using mathematical induction. That's what we said in the earlier part. Right, so let's now talk about how we can formulate the invariant establishment proof obligation. Let's see. Right, let me just have some reminder quickly for you for the init events. So here are some principles you always want to remember when you design the init events. So once you initialize, should never terminate. And also you should always be able to make some progress, which is something about deadlock freedom, which we'll speak about after the invariant establishment discussion. And also event inits simply cannot preserve the invariance. That's something I want you to know precisely what I really meant. When you see the proof obligations formulated as a sequence, you will see that we simply don't have the notion about preserving, because whenever you talk about preservation, you want to say I kind of assume the invariance is actually maintained, is actually satisfied in the pre-states, and then I want to prove that it's maintained in the post-states. But the problem is, for our init event, we simply don't have the notion about pre-states, because before you initialize the system, what really happens before that is simply not relevant. So that's why we don't really say we preserve the invariance, right? You want to be very careful about this. Yeah, because the state before that simply doesn't exist, right? And you only require to establish the invariant for the first time. So that means the post states for the inits is gonna satisfy the invariant. That's really the intuition I really want you to get clear, right? Right. So now let's try to formulate the proof obligation for invariant establishment. And we need some components, some new components for us to really formulate this properly. Let's take a look. So just one new formal components that will be needed, right? Other formal components, you can refer to the earlier slides when we spoke about invariant preservation. We're going to use some of them as well. But this is the one. So the textbook simply used the capital K. I'm not exactly sure what K really stands for. If I find out later, I'll let you know. But remember, I want you to compare this capital K with the capital E when we spoke about the formal components for invariant preservation proof obligation. So the K here, well, the capital E before simply say the effects of a particular events. So you can think about the K here is the effects for specifically just the init events. And of course, in this effects, we can only mention about constants or some literals. We cannot mention about variables, as we spoke about earlier, right? So how do we exemplify this formal component? Think about the K in our initial model, and K depends on only the constant. So you can see here, I'm not listing the variable n. So I really want you to go back to the formal components for capital E and make sure you know the difference between K and E. Basically, in the case of E, you can refer to both the constants and also the variables. But in the case of K, for init events, you can only refer to anything but variables. All right. So here we're saying that the post-state value is going to be, the effect will just be 0. If you take a look, the effect will just be the variable being changed to 0. The right-hand side can only refer to constant or literal, right? Let me emphasize one more. And if you talk about the before-after predicates for the init events action, it's going to be the v prime, all the variable, right? The post-state for all the variables. We have the notion about post-states, but we don't have the notion of pre-states. So it'll be n prime. It's the list contains only one variable, and the post-state value for that will just be 0, right? Right, so that's about the formal component you should know. And now we will be ready to really formulate the sequence for the proof obligation for invariant establishment, right? Let's take a look. So that will be the informal one over here. So we say that assuming that all the axioms, right? Remember, we cannot mention variables over here. There's no pre-states. So that's why the invariant is not really mentioned over here in the hypothesis for the sequence. So we only got axioms, including the constant, right? And we're saying that in the post states, we want to make sure the invariant will be satisfied or established, right? The established for the very first time. And this will be the informal sketch for the proof obligation for invariant establishment. But what about the sequence? You already see in your slides, but let me just show to you over here. So this will be the formal rule for invariance establishment. Somehow the textbook actually use INV, all capitals, for both invariant establishment and also preservation. But of course, if you see the actual sequence, you should know which one we are talking about, right? Let's now take a look. Let me give you a little bit more idea. Okay, let me just annotate very quickly about what I just said. You can see we talk about the formal component K over here, right? You can see K only refers to constant. Okay, so when you talk about effects over here, the effects is specified in terms of constants or literals, right? Like for example, like an integer literal, like a 0, right? And also we talk about the before after predicates, right? And in the case of before after predicates for the action, only the notion of post states is applicable, and there's no notion about the pre-states, right? So that's something I want to mention quickly, and that's the formal rule over here, right? So this part over here, again, it's the axiom, right? And what I want to really emphasize is, you can see over here, invariance satisfy any pre-states is not relevant here, because in the case of invariant establishment for the very first time, we simply don't worry about the pre-state. There's simply no notion about pre-states, right? The pre-state over here is simply not relevant. It's irrelevant. That's something I want you to pay attention to in the hypothesis. And in the consequence over here, you can see we got invariant I over here. I again, that means only a single invariant condition, right? Remember we actually indexed the invariant condition. You can see we got invariant for model 0, number 1 over here, and also for number 2 over here, right? I can be, in this case, 1 or 2, right? So this is only a single invariant condition. Invariant condition, right? And we are saying that the invariance in this case is going to include the constant and also the post-state value for the variables defined in terms of the effects of the init events, right? It's really important for you to know how to interpret this. Let me write it down over here. You can think about this part over here. Okay, let me just box it. Okay, that might be the best way. Okay, so over here, this will be the post-state value. Post-states values of variables with respect to the init's action or effects, right? The before-after predicates. Alrighty. So that's about the rule. It's pretty simple, but you should really know what's really there, and also it's really important for you to know why something is not there, specifically the invariant. You can see the invariant is simply absent in the case of the hypothesis in the pre-state. You should really know why. Right, so I would like to do some exercises together with you, right? Rather than just showing to you the slides about what the invariant, what the sequence should really look like. Why don't we generate them together? I really want to show you the step again. It's really important to see that, okay? So given our initial model M0 over here, right? Just annotate it. So this model M0. How many sequence should we generate for the purpose of the invariant establishment? In the case of the invariant preservation, I listed ML out and ML in, right? But now in this case for establishment, the ML out and ML in, they're simply not relevant, because whenever we want to execute ML out or ML in, we're assuming that the system has already been launched, meaning that invariant has been established. That's the timing when we start talking about ML in and ML out. But in this case, we're talking about init events, right? Only one event to think about. And that event should really establish both invariant conditions over here. So that means we should really generate 2 sequence for invariant establishment. So in general, in some ways, it's actually easier scenario for us, because you only have to worry about how many individual invariant conditions you have. That will determine how many sequence you should really generate for the proof obligation of invariant establishment, rather than multiplying the number of events by the number of invariant conditions in the case of invariant preservation, right? I really want you to know the difference. Right, let's now do the exercise together. We want to generate a sequence from the invariant rule over here, right? So we need 2 sequence over here. And let's now also follow the naming convention, right? So the first one is going to be, so we talk about the inits. So I will simply put inits. That's the name of the events. And then we're talking about invariant number 1. So invariance for model 0 and also index number 1, right? Indices start with 1. That's the convention. And also we're talking about invariance. In the textbook, they didn't actually include the inits over here. They simply leave this part over here empty. But I would say both ways will be acceptable. So in the test or in the exam, if I either leave out this particular part, you only see invariant condition and also IMV, you will know that I'm talking about establishment. But I would say for clarity, I will always include inits over here, at least when I do the discussion, right? So that's something I want you to keep in mind. Right, that's number 1. What about number 2? Let's say for number 2, let me use maybe this. How about orange over here? So that'll be also for the inits events, and it's going to be invariance 0 and then 2, right? INV. So let's now try to do these 2 quickly, and then we'll prove them. And let me just try to highlight them. So the first one we want to do is invariant number 1, okay? And the second one we want to do would be invariant number 2, which will be orange over here, right? Just I'm trying to use the color in a consistent way, right? And let me just separate them over here. Okay, so we don't really get interfered. All right. So how do we formulate this the first one? How do we do that? Well, what we should do is we should have a sequence, right? And the sequence over here is going to have all the axiom. And the axiom is simply just here, which will be D is a natural number. Right? It will be the same for the right-hand side as well. So let's do that as well. The sequence where the hypothesis will just be D is a natural number, right? Because we got the same axiom over here. All right? And now we want to make sure we actually use the individual invariant condition. One will be n is a member of natural number. The other one is n is actually less than or equal to d. However, we want to make sure it's really saying the post states, right? Remember the informal sketch over here. I said invariant satisfied at the post states over here. That's really important to remember. So I'm going to do some intermediate sketch together with you, and I'll show you the final version. So that will be very beneficial in case you're still confused. So what I would like to do first of all is to say n prime, right? So first, let's copy over the invariance. N is a natural number over here, right? You can see that's the first one over here. But we're talking about the post states should really satisfy this particular invariance. And what's the post states? In order to really see the effects on the post states, we know that n prime is equal to simply just 0. That's a before-after predicate, remember? So the before-after predicate, which is also very important, would be n prime is equal to 0. So we can simply now replace n prime just by 0. So this will be the final version, right? The final version will be simply that, assuming that D is a member of natural number, we want to prove that 0 is a natural number. So that's the sequence for invariant establishment for the first invariant condition for the init events. Right? Let's see the second one in a very similar way. For the second one, let's now try to do it. So the second one is over here. So that will be n is less than or equal to d. So that's just a copy and paste of the invariant condition. But we want to make sure it is satisfied in the post state. So that's why we're going to prime it. Right? Make a prime. And then we're going to, and for the sequence, you just cannot have prime. So that's why it's only an intermediate sketch. I'm going to replace the n prime by 0. right? So that'll be the invariant satisfying the post states, which will be defined in terms of this particular literal value according to the before after predicate for the action, right? So that'll be the second sequence over here. Okay, right? So we got two sequences over here, 1 and 2, and they got different names over here following our systematic naming convention. And before I move on to the proof, which is quite straightforward, I would say, but I really want, for those of you who are interested, let's do exercise together. So this is sequence number 1, and this is sequence number 2. Before I move on to proving them, which will be rather straightforward, but I would like you to think about how would you prove it, right? So here is my hint for you, right? I want you to go back to the inference rules that we spoke about last week, right? So these are all the inference rules that you may want to use, right? So I would say pause the video right now and think about, in order to prove those two sequences that you just saw, right? Which one of them? You definitely got access to this inference rule already, right? I'm going to just refer that to you to see which one would be relevant for proving this sequence and this sequence over here. Pause the video and think about it. Alrighty, assuming that you thought about it, I hope at least you will find out which inference rule would be relevant in proving this and also this. Let me now switch to the next page, right? I'll give you one more hint in case you want to do just one more exercise, okay? In case you haven't done. These two would be the relevant inference rules in order for you to really try to prove these two sequences over here, as we spoke about, right? You can now pause the video and think about how to use these two rules to manipulate these two sequences so that they become provable. Right? You can now pause the video. All right, assuming that you've thought about it, okay, let's now talk about it. Well, it's actually rather straightforward, right? Let's now talk about each one of them. For the first one, let me use blue. You can see this part over here, 0 is actually a natural number, right? You can see that. And for P1, we say that 0 is actually a natural number. So this one simply just match. And of course, if you really want, you can also use monotonicity to really drop the sequence, to drop the sequence in the hypothesis. That's something I didn't really list over here, but let me just show to you, right? Remember, monotonicity can drop certain hypotheses, right? So what we can do is we can say monotonicity. Once we apply that, we can have just this. So hypothesis simply gone as if it's true, and then 0 is a member of the natural number. So now you can see this one over here matches perfectly with P1, right? So this part over here is going to be discharged just by P1. So I would say this step over here is also very important, because according to the rule, this part over here should be empty. So if you really want to make sure it's really empty over here, you want to apply monotonicity to really drop this. All right, that's the first one. What about the second one? Well, second one would be, do we need to apply the monotonicity? Well, if they already match, then we don't have to. Let's take a look. Right, you can see here, 0 less than or equal to D, 0 less than or equal to n. You can think about the D over here is the n over there. So the D over here is really matching, somehow instantiating n over here. But the 0 here really matches the 0 over here, right? And also the sequence over here, the turnstile matches the turnstile over here. And then we also got D is a natural number, and also n is a natural number, right? So we definitely are matching. So that's why we don't need to use the monotonicity rule over here. We don't need to drop any antecedents. We don't need to drop any hypothesis, right? So what I really want you to just to see is the D over here is really matching the n over here, right? So D instantiates the n. The variable, the constant D that we are talking about over here instantiates the so-called meta variable in the textbook, but that's okay. So n here is just about the rule. So the rule, you want to make sure everything over here can be instantiated to what you need in your particular sequence. All right. So that's why we can just say that it's proved, but we're gonna justify that. So this one will be if I simply apply P3, and I'm done, right? So both are discharged. 1 and 2, both are discharged. All right, that should be a very, very straightforward proof. And if you go back to the slides, you will see exactly how we can prove it. So you can see these are the two proof obligations, the two sequence with individual distinct label over here. You should really know about a systematic generation for that. And we got the two proofs as we discussed, right? Precisely what I just illustrated on the iPad. And that's about what I want to say about the invariant establishment proof obligation and the generation process. It's a pretty small topic, but I think it's very important because there's so many minor details you also have to watch out for. And think about this more like a reiteration of the process that we spoke about earlier last week. And we're going to apply the same formal process for the next proof obligation, which is called deadlock freedom.